Welcome to breadboarding. In the previous video, we got the main CPU board with all of the clock and reset circuit and all the address, data and control bus buffers all working. And we tested it by setting the data bus to the no operation code 90 hex using this set of pull-up resistors and the little dip switches here. And then we monitored it on the logic analyzer here to actually check to see that the address lines were going up in the way that we expected it to. So this is the Breadboard PC 8088 version 2. And in this video, we're going to be adding the EEPROM, RAM and address decoder in video number 3. So here's our high-level plan. These are the steps we completed in the previous video. The numbers with the hash there are actually the original Breadboard PC video numbers, and you'll see if you go to the Breadboarding Labs channel, if you go to the playlists here, and then you click on the full playlist for the original Breadboard PC, you can see all the videos here. So it means that you can go through some of the more detailed information I covered in these. I'm going to be only covering really the differences in these videos. So this is the block diagram that shows us the basic Nanocomp 8088. This is going to be a basic Intel 8088 computer with an LED display and keypad, so that then we can have a platform to then build out the BIOS and running MS-DOS, floppy disk, hard disk and video cards. And in the previous video, we added the clocks, reset circuit, the bus controller, which was kind of merged with the clock over here, and the buffers and latches, which are necessary to demultiplex the microprocessor buses. There aren't enough pins on the 8088 to drive all the data and address bus lines, and so there are a number of them actually shared between address and data bus. And in this video, what we're going to be doing is adding an address decoder. This is going to produce a number of chip enable, address enable signals, which we can then use to control the chip enables for the read-only memory, the ROM. So this is where we'll initially store our test programs, then the system monitor, the Nanocomp monitor, and then eventually this will also include the BIOS as well, which handles all the power on startup activity before trying to attempt to load an operating system off the floppy disk or the hard disk. Then we're going to add the RAM, the random access memory. Now in this version, I'm actually going to be adding 2 RAM chips, so we can actually have more than 512K of RAM. So we'll initially allocate this to the full 640K address space that was originally available to MS-DOS. In future videos, you might expand that and actually fill in some of the upper memory areas so that later versions of DOS, like MS-DOS 5 and 6, could actually make use of some of the unused memory areas up in the higher memory area. And then in subsequent videos, we're going to be adding the keypad and 7-segment display port, the 7-segment display, and the various decoders and the electronics necessary to drive that. And then the NeoKey 5x5 keypad is one we can buy off the shelf and just need to solder a few connectors on it to make use of it. And then the reset and abort buttons will be directly wired into the reset button line and the non-maskable interrupt on the CPU. So if we take a look at the KiCad schematic, I will put these up on GitHub at some point in time. I'm just waiting to do a bit more work on the CGA card here. It needs a bit of simplification and a few changes to make it consistent with the rest of the version 2 design here. So I'll hopefully do that in the next couple of weeks. So what we're going to need to do here is we've already developed this part of the board here. So we did the control bus buffer, the various address buffers, and the data bus buffers, CPU, the reset power supervisor chip, the 2 oscillators, one for 25 megahertz and another one for 14.3 megahertz, which was the original PC frequency. And this programmable logic device here that I covered in the PLD series, where we managed to make this do the job of both the clock generator chip and the bus controller and managed to merge these into one. So in this video, what we're going to need to do is to add the 2 breadboards above this, and we're just going to do the address decoder. We're not going to bother with all the other chips at this point in time. We're also going to need to wire in our bus rails here. So that was the Vero board, strip board that I've done with about 78-way connectors on that. So that will allow us hopefully a more reliable way of connecting everything up. And then we're going to need to hook up the 2 RAM chips and the EEPROM to the bus rails. Now, I was toying with the idea of whether I needed to add any buffering to these 3 chips, but really, given that we've already got the buffer chips there, these 3 chips are not really going to generate a huge load on the bus. What I was thinking more is that with the video controller and these ones over here, really aware we need the extra buffering because we're adding quite a lot of extra inputs over here. Whereas over here, we're only really talking about 3 chips. So I figured it's probably easier to simplify it and not include some buffering between these chips here and the rest of the bus. So before we have a look at the bus rails, let's just have a quick look at the spreadsheet that I'm using for tracking a lot of this stuff. So we've got the interrupts, the I/O ports, and now I've got the bus pins. So I've tried to lay out the 78 bus pins that we've got here in a way where we've got the odd power rail between some of the sets of buses. But one of the things we could do is add a pull-up, pull-down resistors across a number of these if we needed to at some point in time, should we need to terminate things. So what I've done there is try to work this out so that they all fit with some of the outputs of the address bus buffers, data bus buffers, and also some of the decoder chips. So the order of these bus rails should be in the same order as the pins. So what it should mean is you just use the DuPont cables to go from the output to one side to the other. And I've produced some chip labels for these. So basically just done a very large 78 pin down each side. So a chip label with all of those down each side. Now, if we have a look at the board, what you'll see here, this is the board that we did in the previous video, and now all I've done is I've wired in the various data bus, lower address bus, the address bus A8 to A15, and then the top 4 address lines, so going A16 up to A19, then the control signals, and then up here is where our main address decoder is going to go. And also then the output to the address decoder will also go across to here. And this is our strip board, which has got the 78-way connectors all the way along here. And I've highlighted where the bus rails go in just so I can make sure I line them up properly when I'm doing things. Down the bottom here, we've got where the memory and EEPROM is going to go. So I've got the chip labels for the 2 512K memory chips, and there's 32K EEPROM there. I tend to mount these in a 0 insertions and force socket just because when you're pulling it in and out all the time, program it, then you can bend the pins if you're not careful. So it's a little bit clunky with the ZIF socket there, but it's a lot better than using a chip puller all the time to pull the chip out. So I also need to have a look at the PLD for the address decoder. So this is being based on one of the earlier address decoders, but I modified it quite a bit, and I've adopted some of the best practice that we did in the PLD series. You'll see here that we've got the A19 all the way down to A8 address lines, so there's a few more address lines here, and what that allows us to do is to in fact decode some of the I/O ranges. So we've got a range for the 0 and then the 8 address bits, the 3 in address bits and the 4 in address bits. The 4, we're going to use this for the new 7-segment display and keyboard. 3XX is largely for the external devices, the serial port and things like that, and the CGA card. And 0XX tends to be the system board type devices like the interrupt controllers, the program interval timers and things like that. Then we've got the chip enable for the ROM, the first bank of RAM and the upper bank of RAM. So this will be the bit that will do the 512 to 640K, and we might extend this in future to fill in some of the gaps in the upper memory area. And then we've got the IO read, IO write coming in here, and the address latch enable, which is required for the CGA RAM chip enable to prevent some interference that we had from the earlier series. You can see all the chip labels here are defined with negative polarity. So this means that they're active low, but when we're looking at the conditions here, we only ever have to worry about the true condition. And I'm using the field syntax here that I covered in the PLD video. And what you can see here is by saying the address is made up of the A19 down to the A8 lines, We can then actually specify the address we want for each of these and can specify a range. And what this shows here is the CGA RAM is in the B8000 to BFFFF range. These I/O ports are in the 0 range, the 300 range and the 400 range. And then we can see that the RAM, this is the lower block of RAM, which is 512K. And then the upper block at the moment, we're only using 128K of that, and that will give us our 640 total RAM size for the moment. We could modify this one to include other areas of memory if we wanted to use upper memory area with MS-DOS 5 and MS-DOS 6. And finally, our ROM chip enable is in the top 32K of the address space. So this goes at F8000 all the way up to the top of the memory map. And the last 16 bytes here after reset is where the processor looks to find the first instructions to execute. That normally results in a jump to further on down in the ROM to the BIOS or the monitor. And I've already compiled this, so this is the output, the doc file that comes out of this, and you can see that those rules have now been evaluated into true and falses for the various address lines. The address latch enable is also included in the CGA RAM chip enable. You can see that these address rules makes things quite a lot simpler than it would be otherwise to try and work out what these rules and things are. And if we just check the symbol table here, we can see that all of the pins here, other than the address, which is a field, have got pin mapping, so we haven't got any mistakes in there. And it also has produced the chip diagram down the bottom there, which seems to match up with what we got. So we'll burn that whilst we're actually laying out the board. So what we're going to do now is to start to wire up the RAM-ROM board, and we'll also put in the address decoder as well. So I'm going to speed those up and I will commentate over it, and when we come back we should then be ready to actually start writing the test program to test out the memory accessing both in ROM and in the RAM. Okay, so here's the RAM and EEPROM board. I've just lightly rested the EEPROM on there because it's a lot easier to wire things up without putting it in the 0 insertion force socket there, but the actual position there is okay. The only thing to be aware of is the pins there are slightly narrower, so in fact we get an extra hole on this side over here, but I don't think that's going to matter too much. Now what I'm going to do is I've made up quite a number of DuPont cables. So here's an example of one of the more complicated ones. So one of the problems with the address lines is that they're in a bit of an odd arrangement. So you have A18, A16, 14 and 12 on the top there, and then you've got 15, 17, a gap for write enable, 13, 8, 9, 11, output enable and A10. So what I've done is I've wired these up so that this will go into the address bus in the right order, and then you'll see here there's a number of twists and kinks in this cable, and this means that these connectors will just go in and actually get the right address line to the right pin in theory, so if I've done everything right. So what I'm going to do now is to go ahead and wire everything up. I've already prepared a lot of the wires to fit to size because it takes quite a long time to do that. So I'm just going to wire it up, and when we come back we'll just need to fit the address decoder in the top of the board up in the corner up the top here and program it, and then we should be ready to test the software. Okay, so just put in the power rails. Now the data bus comes down to 5 of the lines there to the right, and then the other 3 are going to go over the other side of the board there. We're just going to wire those down to the other 2 chips, those 3 lines on the top. Now we're going to wire the other 5 lines between the chips down here. So now the memory read, memory write and the chip enables are now coming down for the ROM, RAM 0 and RAM 1. Wire those in to the top of the board up there. We'll just put in the 0 insertion force socket there. Now I'm just going to start wiring in some of the DuPont cables, but I forgot to wire the write enable to 5 volts there. Now we're plugging in the DuPont cables that basically tie all the various address lines together between that side Then we're wiring the data bus in. Then we're going to wire the address lines again together on the top side. Then we're going to wire the lower 8 address bits in there, and then the upper address bits as well. Now we just need to program the I/O decoder PLD. Just got it in the programmer there. Just going to stick a chip label on. So just going to read it to make sure that it's okay. So it's an ATF22 V10C. And now we're just going to load the shed file. So I've recompiled this just to make sure it's okay. I think this is the one that we've just compiled. So this is Breadboard PC version 2 decoder version 1. And we'll just program that and lock bit off. Just move that out of the way. I'm just going to shuffle the boards around so that we can actually see where we want to be working on next. Okay, so our chip is actually going up the top left corner here, and VCC will be towards the top. We need to allow a wire to come around here because we've got this power connector there. So there's enough space for the wire to come around there. The first pin there is CGA RAM, which is going to CGA RAM. So then all we need to do is to wire in the A8 to A11 address lines, which come from down here. And then we'll also need to wire in the 12, 15, which again come from down here. And then the upper address lines, the 4 here, need to go in here. And also need to wire in the IO read, IO write, and the address latch enable. So the IO read and IO write are available from here, so we can just route those to there. And the latch enables here, so we can just route that round to there. And that should be everything that we need. So just wire that up now. Just wire in the power rails. That 5-volt one needs to go around the other side. That's the address latch enable. The IO read and IO write going in there. They're going to wire in the various address lines and the top address lines there. Okay, so that's all plugged in. Just got to put the power rails and things in a minute. I'm just going to put the decoupling capacitors in. We've got to do that on the RAM. So we just put these as close to the ground rails as possible on the chips. Okay, so apart from wiring up the power, we're all ready. So I'll just go off and wire up the power. And I've also got some of these little mini digital voltmeters that I'll put on both the boards just to make sure we're getting good power supply. And we'll now just have a look at the software that we're going to use to test this. So in the original series, I did cover a little bit about Intel 8086 assembly language, and particularly setting up the tool chain. So there is a video here from Slador that tells about how to set up a 16-bit Intel development environment. And the main thing we're going to be using here is a NASM assembler. There's also some of the XT BIOS I used for the reset handling. So this is how to make the ROM package in the top 32K of RAM and get the reset code. And there's also background stuff in the diagrams I'm showing you from that Intel IAPX book. If you haven't done any real mode 8086 assembly language, it takes a little bit of getting used to. It certainly did for me. So I've been familiar with the 6800 series, 6502 and Z80 8-bit processors before, but the segmented memory model here just takes a little bit of getting used to. So although you've only got 16-bit registers on the 8086 and 8088, it does have a 1 megabyte address space, so a 20-bit address range. And the way how it does that is using segmented memory model. And so what the segments do is whenever we work out a physical address, we actually take the segment register and add the other register to it. But the segment register is kind of rotated by 4 bits or multiplied by 16, whichever way you want to think about it. The segment register provides the top bits and the normal register provides the bottom 16 bits, but there is an overlap here, and so in fact you can find lots of different combinations of segment address and the logical address that will actually result in the same physical address. I tend to keep the segment registers with most of the lower bits 0 and just make use of the upper 4 bits when I'm doing things, just to keep things easier. The code segment tells the processor where to find the next instruction, and it combines it with the instruction pointer. The data segment is generally used for general data access and is normally used with registers such as the source index register. The stack segment is primarily used for stack operations such as calling, push, pop, those sorts of things, and also can be used with the base pointer as well when dealing with more complex languages. The extra segment is really like an additional data segment and is often used with the destination index. So when moving data around, you tend to use a data segment and the source index, and the extra segment and the destination index. And the physical address is effectively the data segment times 16 plus the data index. So the key thing we need to be aware of here is that the reset address for the processor is FFFF0. That's effectively 1 megabyte minus 16. And what in fact happens on reset is the code segment register is set to all Fs and the instruction pointer is set to 0. So this means that the effective address is FFFF0, where it looks for the first instruction. And you'll also sometimes see in this notation where the segment comes first and the logical address comes second. So the TESTRAM program is based on the one that I did for the earlier videos, but this one's been updated just to go a bit higher in memory to test the whole 640k of memory. So we're using a data segment register, the destination index register. One thing to note is we can't actually manipulate the segment registers, so if you want to add or compare or test a segment register, we have to copy it to another register first. So let's have a look at the code. It's very straightforward. We're just telling it that we're using real mode CPU. The start address will be F8000, although when we look at the listing in NASM, you don't actually see that end physical address. You do have to do some arithmetic. The top of RAM is now going to be A000 from a segment point of view. This means it will go all the way up to 9FFFFF, I believe, which will be the 640k. So the start is in fact 8000. And if we go to the end first, because this is where reset is going to do, what you can see here is this macro will pad out the rest of the bytes here to the end of the 32k. And what you see here is a jump instruction that will take us to the code segment of F000 and the test start, and then pads the rest of the bytes with FF. And then test start here is where we actually start to do things. Now, you'll probably see in most assembly language to zero a variable generally do XOR it with itself. I think it's slightly shorter and faster, but here I just wanted to keep things plain and simple. So going to 0 AX and BX registers and then move these into the data segment. We actually XOR the data index, in fact. Then all we're going to do is to fill the memory with an incrementing byte value. So for each of the data index, we increment it, and for each of the BL register, we actually increment that. So it's only an 8-bit register. So it will go through 0, but it basically just means we'll get an ascending value, and then it will go back to 0 and keep on going. So basically just go around filling the memory in a 64k chunk first. Then we add an extra 1000 to the segment, so effectively the next 64k chunk. And we keep on going until such time as the segment has actually reached A000, which means we've got the top 64k of RAM. That's filled the RAM with data values. Then all we do is something very similar, just read it back. We're reading it into the BL register, which is not doing anything with it. It just means that when we look at it with the logic analyzer, we should be able to see that the byte value being returned from the data should match the lower 8 bits of the address, is what we'd expect to see. And it will just keep on going around forever until such time as we stop the processor. So it's a very simple program. Basically, the things we're looking for here is that the reset code is at the very end, and then it jumps to the beginning, and we'd expect to see a couple of instructions to initialize these to 0 and then move the value into the data segment. And if we just assemble that, we're just going to assemble that. It's just telling us it's padding this out with FF bytes. And if we have a look at the listing, if we go to the end first, you can see that in fact that this jump instruction, so jump to F000 test start. So this actually is the segment here, and because Intel platform is little endian, you get the least significant byte first, which I always find a little difficult to get my mind around. And the key thing here about the addresses in NASM is that it doesn't actually include the 8000 offset. So in fact, if we added 8000 onto this, we'd end up with FFF0. And what we can see here is EA, 2 zeros, 3 zeros, and an F0 is what we'd expect to see. And then we go back to the beginning. This first bit here is the macro. What we'd expect to see is B8, 0000, BB, 0000, AT, D8. So if we have a look at the output of the binary output and we look at it in hex, what we can do is to go to the bottom first of all, and we can see here we've got EA 0080 00F0. So this is F0008000. That's where it's going to jump to. And then at the top here we can see we've got our B8 and 2 lots of zeros, BB 2 lots of zeros, and AT D8. So this looks like it's all working okay. And what we're going to do is to burn this whole 32K block of data into the EEPROM, and that should give us some code to execute when the processor comes out of reset. It should start doing this, and when we put the logic analyzer on the bus rails and the data rails, we should then be able to see the values being written and the values being read back. Okay, so I've wired up the power. So this is one of the power distribution blocks that I've made in some of the earlier videos, and the breadboarding tips and power distribution videos in the breadboarding playlist will actually include all of that. They've added a connector just off camera up here. Got our mini voltmeters here so we can see what the voltage coming around here. We just need to program the EEPROM first of all, because although we've compiled it, we haven't actually programmed it. So just going to put that in the EEPROM programmer. This one, it does need to be at the bottom, not at the top. So I've selected the ROM type. Let's just read it just to make sure that we've got it in the right way. Looks like it's blank. So just going to choose the bin file. And we don't need to do anything with the loading here because it's just going to go in the start of the 32K EEPROM. You can see here we've got the B800BB00 that we're expecting, and if we go to the end, you could also see we've got the EA 008000F0, which is the jump to the beginning. So we're just going to program that. I'm just going to fit that back in the board now, and then I'll hook up the logic analyzer, and then we'll power it on and see what we get. Just need to make a note that the pin 1 goes at the top here, whereas normally pin 1 goes by the handle, just because this handle was interfering with the cables there. So something to remember. So just need to disconnect this. I'm going to wire in the 32 lead logic analyzer, set that up, and then we'll run it and see whether or not we can see any activity in the ROM and in the RAM. Okay, so I've hooked up the logic analyzer. I was doing a little bit of debugging. I'd plugged one of the cables in the wrong way around, so some of the address lines were coming out incorrectly. So if we go to look at the logic analyzer now, So what I've got here, I've got the A0 to A15, the upper 4 address lines, and the D0 to D7. They're decoded and they're all going to be grouped around here. And then we've also got the memory read, memory write, the reset, and also the ROM chip enable. So what I'm going to do is to set this running, just going to power it on, and this is going to be running for about 5 seconds. So we should be able to see where it's finished writing to the RAM and then it starts to read it back. Okay, so you can see that the reset is high for about the first 400 milliseconds, and then it comes out of reset. So we're just going to drill down first to check that we're hitting the right reset address and then starting the execution of the code. And if we go back to the listing, we know that from our listing that we should have B80000, BB0000, ATD8, and at the bottom, so we'd expect to see at the end EA008000F0. Again, the issue here is that the 8000 offset does not get included in the listing here. It's sometimes a little confusing. So we can see here the address lines for A0 to A15 are FFF0. You can see that the A16 here is 0F, and you can see that we're reading EA008000F0. That's the address where we're going to start the code, and you can then see that we've got 8000 and then B8, do lots of zeros, BB0080 D8. So that looks like it's finding it in the ROM. And if we zoom out a little, we'll be able to see that where we've got the memory writes here, hopefully we'll be able to see when we're writing there, the address is 0000, and we're writing 0. We go to the next write, then we're writing 1. And if we go quite a long way along here during the writes, you can see that the address lines are toggling as we'd expect. So if we look here at this write, we've got 4020, and obviously the byte just rolls around 20 there. So that looks like it's writing all the values. So then all we need to do is to see, can we actually then read the values back? And you'll see that at the end of the memory write activity here, this is where we're starting to read. And the only thing is here is when we'll see up here, this is the code that it's executing. We just need to look for the first address where we're looking at 0. There we go. So we're reading 0, 0, and the value is 0. And then if we just go along a little until we find 1, we're reading 1, and we're reading 2. And if we go quite a long way along here, if we go into the middle here somewhere, we drill down here, you can see here that we've got addresses 3869 and we've got 69. So we'd expect the last 2 digits to be the same in the data. So that all seems to be working. So we've managed to get the TESTRAM program to write to all areas of the RAM, and it sort of goes through the whole 640K of memory, and also then check that we've been able to read it back again. So we've completed these first number of steps here. In the next video, we're going to be looking at building the LED display and keypad, and we'll also be updating the test code here to poll the display and poll the keypad. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe, and if you found the content interesting, please hit like. It just helps to make the videos available to more people on YouTube. Thanks for watching.